Okay, let me get started. The purpose of this video is to show how to make the various plots here in this predictXLS file. All the files in this, I'm going to be using all the files in this directory, which you should have a copy of. And the predictXLS shows a number of our validation spreadsheets that compare experimental data to the OLI predictions, and I'm going to go through each of these plots and show how they were made. Now I should note that it is possible, I'm pretty sure, to make these plots using the stream analyzer, although at times it can be a little bit difficult, since in some cases the OLI predictions would have to be made point by point, in that I don't believe you're able to do it now as a survey. So instead of using the stream analyzer, I'm going to show how we use the regression program in a calculation mode. And that's actually what was done. I have files that were used to make each of these plots, and I'm going to show how to use the regression program. Now, the regression program is run from DOS, and I have a file here, course.doc, that shows the various commands that you have to use, the steps, and then the individual commands that you have to use. The first thing you have to do for anything is you have to create a model file, and we'll go through this for each example. This is kind of hidden behind the scenes in the stream analyzer, so you're probably not aware that it's being done, but it actually is doing the same thing. And in order to create a model file is essentially just a list of all the species for a particular model, and we'll do that. We'll actually use one of the OLI programs, OLI ESP, and like I said, I'll illustrate that. Now, once we have a model file, if we have to make changes to it, then we may have to run the last step of creating a model file, which is the OLGen, and that we do from DOS. That's the second step here, where we regenerate the model file from the command prompt, and I show the command prompt for that, OLI, OLGen, the mod file name, and the database name, and then I have an example down here. And when we then run the regression file, which is actually the INR file that contains all of the calculations that I want to do, we do OLI regress, and a mod file name, an INR file name, and again an example. And this file, I'll just, you have it as a reference for the various command lines that you may have to use. One of the things that you'll notice is that it uses this OLI command, which is actually a BAT file, which I have included here also. We can take a quick look at that. That just points to the directory where the OLI files are, and you have to make sure that it points. I'm pretty sure this points to where it's usually installed on your computer. If it isn't, you might have to change this. Out here we have this 8.3. If you have a different version, you might have to change that. But all it is a bad file with holders for the various entries. And then again, we'll be using that file fairly often here. Now back to the Excel. Okay, the first plot we're going to make is the solubility of sodium nitrate in water. Validation plot is shown here. If you go over to the left, you can actually see what's in this plot. It shows all of the experimental data here, and at the top that are the points here, and then at the bottom it shows the OLI predicted values. And the file that we're going to run here is what's going to create all these calculated values. So the first thing we have to do is to create a model file. Let me open this thing back up again where the course is. And this system just has NaNO3 in it. So to create a model file, we'll use OLI ESP. So we open up that, and we just select the first thing here, ESP process. And but all we're going to do here is create the mod file. We select that. It's a new process. I'm just going to give it an arbitrary name. We're not going to make it run. We want to build. We want to make the chemistry model. So we select that. It's going to be a brand new model, and I guess I'll call it NaKNO3. Well, no, just NaNO3. That's all we have in here. We're going to do all this with the MSE, which is mixed solvent. So you space down and hit. It has instructions. You hit the space bar to select that. We're just going to use MSE Pub. We're not going to use any other special data banks. And then we have to list the inflows. And in this case, it's only NaNO3. Type in that, press enter. That's the only species. So we'll press, once we're done, we press enter again. We can select some options here. Again, we'll just use what's already shown. We want to include a vapor phase as well as all the solid phases. Those have already been selected. And we press enter again when done. And again, it's created the mod file. And now we're going to create the it's actually the DBS file that's used in that takes all the information out of the data bank. So we press enter again. It's gone through, and now we've created the mod file. We exit out of here. That's the only thing we have to do here in OLI ESP. So if we go back to our course directory, we can actually look at the mod file we've just created, which is this, and it shows all the various inflows, all the species that are included in the model, the vapors, aqueous species, ions, the solids, hydrates, all of the equations it has to solve. For the time being, this is just, well, the software needs it, but it's just something, and that might be useful to take a look at if you wanted to see all the species that are involved for a particular case. Now, we'll go back to what we're actually trying to accomplish here, and the first thing to making this, or the first thing I do when making a solubility plot, is to calculate the endpoints and the invariant points. And invariant point, the first one is right here, which is where the ice line intersects the NaNO 3 lines. We want to calculate exactly where that occurs, and then all the way up here at the top we have the melting point of NaNO3, which is at 100% NaNO3. And to do that, I've created a file here that shows how that is done, this one. And this is a regression INR file. Now, we are not going to be doing a regression, so there's a lot of stuff we don't have to worry about. The only thing we have to do is for up here underneath control, where you specify the maximum number of iterations. We're just going to do a once through a calculation, so I just set the maximum iterations to 0, and also we are not going to be regressing any of the parameters. We're just going to use all the parameters that are already in the data bank, so we don't have to put in any of those as well. And then we have data sets, which are actually used to put in data to regress, but in this case we're just going to put in points that we want to calculate. And as I indicated, we want to calculate the invariant points. So the standard calculation here is to specify the temperature and the pressure and the amounts of all the inflows, and then the program will then calculate what phases exist and how much is in each phase. But we don't quite want to do that. We want to fix other things and free up the standards things. So the first thing here is all of the calculations here are going to be done at what we call the bubble point, where we only have a very small amount of vapor and everything else remains condensed. And in order to do that, we fix the vapor rate at a very small number and free up the pressure. So the program will calculate the pressure that is right, such that it's right at the bubble point. And that is done in each case here. In addition, in order to calculate these in invariant points, the first invariant point is where we have both the ice and the NaNO3. So what we want to do is to fix those amounts at very small numbers, and then have the program calculate both the temperature as well as the amount of NaNO3 that it would take in order to meet that condition. Furthermore, I'm going to be doing all of this on a molality basis, so I specify the amount of water as 55.5 moles, which is exactly 1,000 grams of water. So I have that in each case. And then on the calculation line where you actually put in points, I'm specifying, and in all cases here, since this is all being freed up, this is actually just an initial guess, so I just put in an initial temperature and an initial amount of NaNO3, but these are actually going to be calculated in order to achieve what we specified on the fixed line. The first data set calculates, like I said, the invariant point. Second one is we want to calculate the melting point of NaNO3. And in this case, again, we're going to free up the pressure, fix V, and we're going to fix the NaNO3 at a very small amount and free up the temperature, which is what's being done here. But this time we're not going to free up the NaNO3. Actually, that's going to be input as 1 and it won't be changed. And I only put, actually I just noticed here, there's a very small amount of water here, so this is essentially a pure NaNO3, and then we put in an initial estimate for the temperature. Now I'll explain. When we run the regression program, it actually produces a number of output files, which we'll briefly go through, but the most important, a useful one for what we're trying to do here, it produces a CSV file, which is actually an Excel type file. It already contains a number, some information in it, especially the stuff you've input, as well as some things that have been calculated. But you also have the option to specify additional variables that you might want to include in the CSV file. So in this case, I've specified T, which is the temperature, the inflow for NaNO3, as well as the amounts of the two solids, and those will then show up in the file. So now we have our mod file. This is the file we're going to run. We go into DOS, and you have to be at the directory that contains your input file as well as the mod file, which I already am. And now we're going to run this first regression file. And it's OLI, regress, the name of the mod file, NaNO3, and then the name of the file, the INR file, NaNO3PT. Press enter, runs, it's already done, and it's produced some output files. We're not going to do anything with the PLT file. The OUE file, if you wanted to take a look at it, shows a summary of your input, and then it gives the old electrochem style of output for each point that is done the calculations on. If you want to take a look at it, at the end of the thing, it prints out all the output variables and the minimum and the maximum values. We're really not going to do anything with that. There's also an NRM file, which is very useful for doing a regression, but since we're not, we won't pay much attention to that. But the thing that is helpful here is the CSV file. If you open up that contains a row for each point that you've asked it to do the calculation. And it includes the calculated values. Well, actually, what's useful here. These are regression type of information. It has a converge flag, which can be helpful if it's equal to 0, it means the points converge. And it's also a helpful, one of the columns that might be interesting is the phases. These are the phases that are present for each point. So we have a liquid, a vapor, and a solid. Now remember, we only specify the tiny amount of vapor and the tiny amount of solid. So it's all in the liquid phase. This is a calculated temperature. Now these are actually in K. The first T is the input value. This is the T that I actually specified on the CSV line, and I'm going to convert that to degrees C. So now we see the value. This is the temperature that was calculated by the software. This is the amount of NaNO3 for the first point. Remember, it was calculated. Second point, it's pure NaNO3, and then this just shows us what solids are present. So you remember the first point was the invariant point where we had both ice and NaNO3, and in order to get that, you have to be at this temperature and that amount of NaNO3, and then for the melting point of the NaNO3 it calculated this as being the temperature. So we now know the exact points for the invariant points, so now we can actually calculate the rest of these two. We can complete the line here, and the INR file that's used for that, which I've already set up, refresh this again, is NaNO3 predict. Now I've included this. This was the first invariant point is included here. That was this part. So now we know exactly where that is. So in order to calculate the ice line, we add in a bunch of extra points here. And to calculate, now we only want to calculate the solubility of ice, or how much NaNO3 we have to put in order to get ice. So once again, we're going to do it at the bubble point with 1,000 grams of water, but now we only want to fix ice at being a small amount and free up NaNO3, and we're going to do it at every degree. So I just put in -1 to -17. We know the invariant point ends here, so we'll go up to -17. And again, for NaNO3N, it's only an initial estimate because that's going to be calculated. So these are all the points to generate this part of the curve. Now the rest of the points for this part of the curve is shown in the second part. We're now again 1,000 grams of water. We're at the bubble point. Now we're going to fix the NaNO3 at a very small amount, and again free up the NaNO3. And we're going to do this at every temperature from the invariant point all the way up to the melting point, 321. And once again, we include the calculation to calculate the melting point. And what else is helpful here? One other thing that might be useful I can show you how I do it. As opposed to having to type in all of these numbers, you can very easily do it in Excel. And let me just illustrate that. Just go to an empty file here. Let's create, let's just say, a bunch of points from 1 to 100. I type in 1 out here. There's egg 1 plus 1. I can create, well, I'll just go up to 100 degrees. You can change it however you want. And this is my initial estimate for NO3. So what I'm trying to do is match up what I have here in the INR file by putting in the temperature and the NO3. So I've created that in this Excel file, and then you can just copy these points from Excel into your INR file. And the one other thing you have to do is, when that's done, it inserts a tab between each column, which we have to change into a space. So in order to do that, I just highlight that, copy it, and then I want to change all of that. So I've pasted in the tab symbol, and I want to change it to a space, find it, and replace. I'll replace all of it. So now I've converted it over to INR style input. So that's how we could just as easily, that's how I would have created all the points here, say going from minus 17 to 321. Now I'm just going to delete that because we're not going to use it, but that's just an example of how to very easily create a bunch of calculation points, kind of like, like if you're doing a survey style calculation. I'm not even going to save this actually, because it's all, at least I'm not going to save the changes I made from this actually. So I'll close that. Now, okay, we're going to run this file now that will create all those points. It's pretty much the same. It's NaNO3P. Take off that and run it. There's a few hundred points it's trying to calculate, so it shouldn't take too terribly long. When it's done, and we can now look at the CSV file, I guess. It now shows it has a row for each point. Has all the points here. This shows the points where we had ice. There's the NaNO3 points. This row here is the first invariant point where we had both of them, and then down here at the bottom is the melting point where we just had the ice. I mean, we just had NaNO3. And these are all the temperatures. There's your NaNO3 flows on a molality basis. And this is actually what's in this NaNO3 line. Down here at the bottom we have the prediction, we have the temperatures, we have molalities, which is the last column here, over here. And what I've done is convert them to weight percent, and so you can just copy these columns. Actually, you have to remember you have to change a temperature from K to C, and then you convert these molalities from molalities to weight percent. If you plot it on a molality basis, which you can do here, you see that as you approach the melting point, for almost pure NaNO3 is very high, but when you convert it over to weight percent over here, it's possibly easier to show it like this. Then it looks like our plot. There's actually an equation here that then now converts molality to a weight percent, and then you plot it, and you get this curve. So that is how we created the first plot, which is the which is the solubility of one salt in water. This is actually a fairly a simple one. So the next thing will be to look at the more complicated solubility in water, which I'll do next. Okay, now we're going to look at the second plot in this Excel spreadsheet, the solubility of magnesium nitrate in water. This one is a little bit more complicated than the sodium nitrate in that we have a number of hydrated forms of magnesium nitrate that form. Again, if you go over and look at the experimental data, and then down here for the predictions, you see first there's ice, and then we have a 9, a 6, a 2 hydrate, and then finally the anhydrite, or the unhydrated version, magnesium nitrate. As before, the first thing that we need to do is determine the invariant points where it switches from one solid phase to another. So again, as before, the first, but even before that, what we have to do first is to create a mod file. So again, we'll run OLI ESP process, new process, just arbitrary name A. We're going to create a new chemistry model, and I'll just call it magnesium nitrate. Make it consistent. Select MSE. Don't need any special data banks, and put in the inflows we have, which is magnesium nitrate. That's the only species. Press enter. Again, we'll use all the defaults here. Continue. Continue again. And now we've created the mod file. Escape out of here. And if we want to, again, you can look at the mod file. It shows the inflows, all the various species that can form when you dissolve magnesium nitrate in water, the aqueous ions and the solids, and then at the bottom it shows the equilibrium equations that OLI is trying to solve. So we have the mod file, and again, the first step is to get the invariant points. There's one here, and one out there. So I have a mod file that I've already set up, or an INR file, which is this one, I believe. Yeah. And it's like the one we had before for the sodium nitrate. We have a data set that we use to calculate each of those points. The first one here is for where the ice switches over to magnesium nitrate, 9-hydrate, and we do all the same things. We have water at 1,000 grams, and we're doing everything at the bubble point, and we're going to free up the amount of MgNO3 and the temperature in order to get both the solid phases. And then the next step, kind of the same, but now we're going to find where it switches from 9 to 6, and then from 6 to 2, and the last point here is where it switches from the 2-hydrate to the unhydrated version. So now I'll run that file. OLI, regress, the mod file, and then the regression INR file. T. It's done. Then we'll open up the CSV file. And you can see I'll convert temperatures in K to C. And now we have the temperatures in C and the amount, the molality amount of magnesium nitrate that it's calculated in order to show each of the, where we have each of the transition points going. This is the first one, the second, the third, and then the fourth. We now use these temperatures, and now we know where this point occurs. Actually, there must be another one in here. I think there's one down here someplace. Oh, at minus, okay, we also have a transition around here too. So there's one solid here, another solid, a third solid, and there's the fourth. So now we know where all those occur, so now we just have to fill in a bunch of additional calculation points in order to determine the curve between each of the transition points. And that is done in, not that file, that's done here. So now for ice, we're going to go from, according to this, it switches over at around minus 33. So now we're going to calculate ice points from -1 to minus 33. Then I've included, here's the invariant point between ice and 9. Then we're going to calculate 9 from minus 33 to minus 15, which should be what, minus 14. Another invariant point, then the next a solid from 45 to 123, the last invariant point, and then the final solid up to 200. And again, these are for the single solid solubility calculations. We're actually fixing the temperature. We're like doing a survey with the temperature, and then we're just calculating the amount of magnesium nitrate that will dissolve until you get just the first bit of a solid phase. So now I can run that file. Which we'll do here. I guess I misspelled something. And I did. Okay. We have to use the correct INR file name. We get the usual output files. Open up the CSV, and now we have a lot of points along the solubility curve, all the points where we have ice, and then 9, and then the next hydrate, and the next one, and the next one, along with the invariant points, temperature, and then this is the inflow that was calculated. Now the one you notice on this plot, we have some interesting curves now. So if we actually plot this solubility versus the temperature, we have these gaps. And that is, if I can show that, the first one. The first one actually occurs here, going from 317 to 317.79. We have a big jump in the solubility, and that's actually what it's done. It's calculated the curve up to, this is around 45C, up to here, and then it's jumped up to here. It's completely skipped this entire part, and that's because we've been doing this at fixed temperatures, where we just increment the temperature by one degree, and then calculate the solubility at a fixed T. In order to get this part of the curve, we actually have to reverse the calculation and fix the solubility and calculate the temperature. So, for example, we need to do a bunch of points between about 5.5 to 14, and that's what I've done in what is the final file that I use to calculate magnesium nitrate, which is this one. It has all the same points as the previous file, but I've now added a section here, this piece, where this curve here, this is 6-hydrate. So I've added a piece here. This is all the same as this part where we free MgNO3N and fix the 6-hydrate solid, except now we're still going to fix the 6-hydrate, but instead we're going to free up the temperature. It's going to calculate the temperature. So now on my data line, the MgNO3N that I specify won't change, but the temperature is now just an initial estimate, and it's going to be calculated. So we have to do that for this part of the, didn't want to do that, this part of the curve, and then there's also actually a small piece right up in here where we also have a gap, and that's the next one here. This piece fills in all of those points. So now we can run this final case. MgNO3P. And we should get the entire curve. Finished. CSV file. And we just plot the solubility versus the temperature. We see we have points all along here. Everything's filled in. So now you can just, there's the curve in terms of temperature and K. The magnesium nitrate is in molalities, so you can convert that to C and weight percent. And just like before, I have columns here. I've already converted them to C, and there's molality, there's the equation to convert it to a weight percent, add it into your Excel spreadsheet, and you can plot it, and you end up with this final plot here. So that's how we do magnesium nitrate. Okay, the next plot that we're going to look at is the solubility of sodium and potassium nitrate in water. And here's a plot of the experimental data versus the prediction for a number of isotherms. Now, first of all, we have to make a mod file as we did before, and we'll follow the same steps. Process, chemistry model, a new model, and this is sodium and potassium nitrate. Again, it's MSE, no special data banks, NaNO3 and KNO3. Enter, take the defaults, continue. And one more time. Now we have the model. In this plot, one thing I want to point out is that for the lower isotherms up to about 100 degrees. This green line, we only have either the sodium nitrate being a solid phase or potassium nitrate, but at higher temperatures, actually about 150 and above, you notice these points here where what actually happens there is we have a double salt that can form, and that is present. That's been added to the mod file. We have the usual inflows, all the species and equations, but we have a double salt, which is this thing: sodium, potassium, nitrate. The equation for it, it's in equilibrium with the sodium, potassium, and two nitrate ions. Now, just like with the solubility of one salt in water, for where we had to first determine the invariant points, we have to do, or for the purposes of creating this plot, I calculate the invariant points here as well. That would be the points, like for example here, at a certain composition of both the sodium and potassium nitrate, you get both solids in equilibrium. The point here, there, and continuing out to here, and then at these points here, you actually have points where it's in equilibrium with the sodium nitrate and the double salt, and then out here it's in equilibrium with potassium nitrate and a double salt. So the first thing we have to do is to calculate the concentrations that form all these invariant points at each of the temperatures. And so I have a file. The file that does that is this one. Yeah, this is the file where I calculate the invariant points. So up to 125 degrees, I want to calculate the amounts of the sodium and potassium nitrates that I need in order to form both of the solids. So I fix each of the solids at a small amount, and I'll free up both inflows for the sodium and potassium nitrate. And as before, I'm doing things with 1,000 grams, all on molality basis and a bubble point. Now above 100, and then we have to do this calculation for each temperature that we want to plot. Now above 125 degrees, we actually have an additional solid. So first, for the three highest temperatures, I need to calculate how much of both salts are needed to form the first invariant point, where there's both the sodium nitrate and the double salt, and then the concentration of the two salts to form the double salt and the potassium nitrate. So this file is used just to find all these invariant points. So now I can run that. Using the new mod file, KNO3, NaKNO3, that's done, CSV file, we can see for each of the temperatures, we now have the molality concentrations of the potassium and the sodium nitrate, where we get to a solid phases. Up to 125 is the sodium and potassium nitrate, and then at 150, 175, and 200 we have two compositions, one for each of the invariant points. Now with these compositions here, these are now used to create the additional points to fill in all of these lines. And we have to do it for each isotherm. I'll illustrate one of them, or a couple. I already have all of this here, and I guess it's probably this file. Yeah, okay. So I've added quite a lot of calculations in here. First, we're going to calculate these lines here where we have the solubility of the sodium nitrate. So here, what I do is fix only the sodium nitrate, a solid phase, free up the sodium nitrate in, and then for each isotherm I'll do it at a bunch of fixed potassium nitrate concentrations up to the invariant point. And I do that for each isotherm, going up, well, for all of the temperatures. You can space out the concentrations of for the potassium nitrate as you wish. We go up. I've included a lot of points in here, and then I have, once again, these are the invariant point calculations again that we've already done. I include them here. More invariant point calculations, those and those, and then additional concentrations here. Here's, in order to calculate these three pieces of the line where we have the double salt, that's what's being done here. While free up the sodium nitrate, fix the double salt at a small amount, and ask it, and then fix the potassium nitrate at a variety of compositions that fall between this point and the corresponding concentrations here at 150. So for example, at 150 degrees, I'll vary the potassium nitrate from 67 to about 90, which is what I've done here, 70 to 90. Do that for each of the isotherms, and then for the last part of the curve, for the solubility of just potassium nitrate, all of these curves along here, that's what's being done in this part. Now I fix the potassium nitrate at a small amount, free up the potassium nitrate inflow, and then hold the sodium nitrate. I do that at a bunch of fixed sodium nitrate concentrations. Now, there's a lot of points here, as you can see. I usually put these into an Excel. I set up the calculations, these particular lines, into an Excel file and then just copy them into here. The last thing here, actually, this is another interesting point that can be calculated. There's obviously a temperature here somewhere between 125 degrees and 150 degrees. There's going to be a temperature at which there'll be an invariant point at a certain temperature and for a certain amount of the sodium and potassium nitrate at which all three of the solids will be in equilibrium at one time. It would be the lowest temperature at which the double salt forms. And if it's of interest, that's actually what this last data set is going to calculate, where I now fix the amount of all of each of the solids at a very small amount and free up both inflows as well as the temperature. So I would actually plot that point on here, but it might be a point of interest that you can have the software calculate. So then we just run this file. This one takes a little bit longer because there's an awful lot of points here. It's the same one minus the t. Close this. I think this takes a minute or two. I'm not. Quite a long time. Wow. See if it is running here. It's working, it's just a lot of points, I guess. Oh, okay, finally. Wow. So now we can open up the CSV file and Well, you can, just a few ways to do this. I guess one easy way would be to sort this by temperature, since that's how we're going to make the plots eventually here. What are this took so long? Wow. By temperature. So now we can see for 0 degrees here, which are these points here, we have the molalities of potassium and the sodium nitrate, and then first we form the sodium nitrate solid, we have the invariant point, and then potassium nitrate. And if we say were to do a quick plot for the compositions here for 0 degrees, we get if we plot molalities, it looks like this. And we could plot other isotherms. And in each case you can see which solids exist down. Let's see, if we go to 150 degrees, for example, first we get the compositions for the sodium nitrate, then we have an invariant point for the sodium nitrate and the double salt, and then just a double salt, and then the invariant point for the double salt potassium nitrate, and then just potassium nitrate. The molality plot looks like this. You can obviously put as many or as few points along these curves as you want. I seem to have included a lot here. So on a molality plot, you have the sodium nitrate, the double salt, potassium nitrate. Now, I've then moved, or these are the calculated points then that exist at the bottom of this file, where here's the predicted points, and we have molality for the potassium and the sodium nitrate, and then again I have an equation where I convert molality to the weight percent. Here's a conversion to the weight percent for potassium nitrate, and then out here is the sodium nitrate, since I put each isotherm in a different column for the purposes of the plot. And then you can plot that, and this is the curve you get. That's what these points all give. Now, the one thing I mentioned here, the last calculation in the INR file was that invariant point where we had all three of the solids. Actually, the easiest way to look at that is we'll just look at the OUE file. At the last point in this file is that calculation. So it calculated that the temperature is around 138.5, and then here's the molality concentrations for potassium nitrate and the sodium nitrate, and those are the conditions that are required. You see that we have a solid phase. Here we have all three of the solid phases: the potassium nitrate, the double salt, and the sodium nitrate. So that is how, and this case here we actually have a common anion, but the procedure, whether or not you have a common ion or not, the procedure for doing these curves the way that I do it is the same for a binary system. So that concludes the sodium and potassium nitrate plot. Okay, now we're going to look at this. We're going to switch to the next plot now. This is the water activity along the saturation curve for the sodium nitrate potassium nitrate system at 90 degrees. And this would be a curve here between the 90 degree curve would fall here between the 75 and 100 degrees, so it would be somewhere along in here. And this is a plot of the water activities then along that curve. So we would start here at this end. This would be the pure, or the potassium nitrate dissolved in water, and then over here this is the sodium nitrate dissolved in water, and then down here is the invariant point where you have both of the solids. Now the construction of this curve, actually the calculations are exactly the same as calculating the solubility that we had to do in order to make this curve. So that file is this one. This is the INR file. Actually, before I do that, we have to make a slight adjustment in the mod file. We're going to use the same sodium potassium nitrate mod file, which is this one, but we're going to add a define for the water activity at the end of this file, and I have that down here in this file. We're going to copy that into this mod file. We have to put it here at the end. So now we've added a new section here. If it's called equations, where you can in essence create your own variables by doing Fortran calculations using existing variables. And here we're taking these are variables that already exist in OLI. This is the log of the mole fraction of water. This is the activity coefficient of water. We add them together, take the exponentiation of it, and that's the water activity. So we've added that into the mod file, which we're going to now save. And we're going to use, this is one reason why to use OLGen. We now have to regenerate this mod file, so we're going to do that using the OLGen. Since that's that's OLI OLGen, the name of the mod file, and then the data bank we're going to use, which is MSEPub. Now we've regenerated that file. Now we can go back to the INR file, And this is, again, this is the same type of calculation that we used before, except now we're going to calculate the solubility at 90 degrees. So we have a section where we're going to determine the part of the curve where NaNO3 is the solid. Then we have the determination of the invariant point, and then we have the determination, the rest of the curve here, where potassium nitrate is the solid. And up at the top here on the CSV line, I've added out here at the end this new variable W, so now we're going to include the calculation of the water activity at every point along this curve. So we can now run that, same as using regress. What's this file called? This is, yeah, okay, this is the one. KNO3AP. Run that. Now we open up the CSV file, and we now have a column here for the water activity along each point, where we have first the sodium nitrate, invariant point, potassium nitrate. It's not going to look quite the same as this plot, but let's say I plotted first as NaNO3. This plot is actually done on a water-free basis, so this is just the mole fraction of the sodium and potassium nitrate. So you can take the molalities here for the sodium and potassium nitrate and convert them into just mole fractions, and then plot the water activity, and you get this plot. And experimental data is also included here, which, yeah. So that's how we created this plot. Okay, now we're going to take a look at the last three plots here, the ones labeled OR, NL, AW1, 2, and 4. These are all pretty much the same. This is actually a representation of an experiment where you take a certain salt or a certain fixed composition of a number of salts and dissolve it in a large amount of water. You then, so that it's almost infinitely dilute, you then evaporate off the water, and at certain points measure the water activity. The first plot here is for just a single salt, magnesium nitrate, and it shows what happens as the water is evaporated off. As you can see, the water activity drops and gets quite small as it becomes more and more concentrated in magnesium nitrate, and actually it reaches the point you can't tell here where it starts, where a magnesium nitrate solid begins to form. It's easier to see here on the next plot where it's a certain composition of the sodium and potassium nitrate. You can see as it begins, as you evaporate off water, it hits this kink point. This is where a solid begins to form, and then there's way out here at the end is another appearance of a solid. Now these are actually fairly easy to calculate. You could probably even, actually I think this can be done fairly easily in the stream analyzer, although you do have to come up with each point probably individually. But now I'm going, okay, actually before we look at the INR file, I'll show how to do the first one. We have to make the same modification to the mod file that we had to make before. The first one is magnesium nitrate, so there's already an existing mod file for magnesium nitrate, which I'll open up, and then we have to add a define for the water activity, which I will do. Add it to the end of this file, and then we have to OLGen. We have to run this file through again on OLGen. That is done. Now, for the first plot here, the magnesium nitrate, that's ORNL1, and this is just a fairly simple calculation. It's just being done at the bubble point, and it's at the same temperature, 100 of, I guess all of these are actual experimental data at 100 of 40 C, and all that's being done is I just changed the concentration by 1% each time. So it starts out with pure water, and then it drops down 0.99 water, 0.01 MgNO3, and then on till we get to 0.6 water and 0.4 magnesium nitrate. And again, you notice that I've added the water activity to be included in the CSV file. And these are plotted. Total parent salt mole fraction. Yeah, so this is just the mole fraction of the salt. So we can run this file. ORNL1. It's done, and this one I think we can almost, yeah. If we plot the water activity versus the magnesium nitrate now. Yeah, this looks almost exactly like what's in that plot. So that's how this one was calculated. The others are the same type of calculation for ORNL2 here. This is for a mixture of sodium and potassium nitrate. And this is a, well, again, let me regenerate the mod file. I have a sodium potassium nitrate mod file here someplace. Which actually we've already, that's right, we added the water activity to it for the earlier plots. I don't even have to change that now. And this is again, a ratio of the sodium nitrate to potassium nitrate is fixed. So that's always the same, but I'm doing the same type of calculation here. It's at the bubble point and all. I'm just going through and decreasing the amount of water by a 0.01 each time, and then increasing the amount of salt. And these points can be easily prepared in an Excel spreadsheet, which can then be copied over here, as we did in one of the earlier plots. And so now I can run that. I think this is NaKNO3 and ORNL2. Done. And now we have the water activity. Actually, to make this look like this plot, we have, I think if I create a column 1 minus water, that would be the amount of salt. So if we plot the water activity versus the salt concentrations, we get the curve that's shown in the spreadsheet. And you can also, I've added at the top of, as I had done in the other file, I've added the solids that can form are also included in the CSV file, so you can see that as you decrease the amount of water, you eventually hit some points where you get a solid phase. First you get this sodium nitrate, and then you get both the sodium nitrate as well as a double salt. And that's the two kinks here in the curve. The same thing is also shown in the magnesium nitrate file. You can see if we go back and check that one, we see which solid was formed, or we see when it forms. It actually doesn't form until it gets fairly concentrated. You start getting some magnesium nitrate. I guess only a couple other things here. At the end of this file, as well as the magnesium file, there's a calculation. I've added a calculation to determine exactly when you first form a solid phase. For example, here in the magnesium nitrate one, I've fixed the solid that forms at a very small amount and freed up the H2ON, so it calculates exactly the amount of water that is present just when it first forms magnesium nitrate. And then I've included the same calculation here for the sodium potassium nitrate to determine at exactly the amount of water where you first form the sodium nitrate, and then how much it also needs in order to, when you first form the double salt. So those are added at the end of the calculations. And the last plot here I'm not going to run. It's actually a multi-component mixture. There is an INR file for it. It's sodium chloride, potassium chloride, the sodium nitrate, and potassium nitrate. Again, all the points, it's the same ratio of the salts, and I created these points in here again from an Excel spreadsheet, and when that is run, you get the final curve here. And that is, those are all the plots, and you should have all the